Evaluate the surface integral. S is the cone with the parametric equations given. So this is of a function f of xy, z. So we're not looking of a surface integral of a vector field, we're looking at a scalar field, and that's what we represent this as. Now, this is going to be important, but what we also need to know is how we can take something in this form and set that equal to something in terms of u and v. So like we don't like this ds too much because it's not, you know, you can't just use that to integrate. It's not really helpful. So we want something like dA, and the way you convert is, and if it's parametrics, which it is right now, just like the last example was, it's just f of r u comma v times the magnitude of r sub u cross r sub v. So that's just the formula. So remember, r of u comma v is just u cosine v, u sine v, and u. R sub u of u comma v is, treating v as a constant, is cosine v, sine v, 1. R sub v of u comma v is treating u as a constant, negative u sine v, u cosine v, and 0. Let's take their cross products. I, j, k, and then you have, so it doesn't matter the order, of course, as I mentioned in the previous video, it's the magnitude, cosine v, sine v, 1, negative u sine v, u cosine v, 0. So r sub u cross r sub v is 0 minus u cosine v I minus 0 minus negative, so it's positive, so sine v, and then j plus u cosine, I think that's a v, yeah, that's a v. That's a v too, I believe. It is. That looks very much like a u. It's a v. Cosine v. Cosine squared v. Because it's u, yeah, u cosine. And then minus negative, which is positive, u sine squared v. That's pretty nice because what this is going to become at the end of the day, negative u cosine v, negative u sine v, and then this is, okay, I'll just do this out here, but you should see this immediately at this point, u sine squared v. We can factor a u out, and why am I doing that? Well, because of this identity, this trigonometric identity. That says that this is 1, and so this is just u. That's a very nice identity. It really simplifies a lot of your work for many problems, not just this one. Especially useful with when you have like r's and thetas and stuff. Very useful. Anyway, this is u. It's useful, of course, with trigonometric, when we have trigonometric functions, because of the fact that it's trigonometric identity. Anyway, we can go ahead and find the magnitude, and I'll do that up here. Okay. Square root of, so I'm just gonna write this as negative, so negative cosine, negative cosine v squared plus negative u sine v squared plus u squared. So that's going to be u squared cos squared v, u squared sine squared v, u squared. This can be factored out again, so it's just u squared, and then that's 1 plus u squared. That's unnecessarily long. Let me make that shorter. U squared plus u squared, 2u squared, which is root 2u. That's what's going in here. Now we want to convert f of x, y, z, which I actually wrote up there. Again, I'm writing it, to f of r, u, v, which is just equal to x is this, so it's u cosine v times y is this, so it's u sine v times z is this, it's u cubed cosine v sine v. There you go. So that's the integral over d of, let me see, let me go back up, sorry for that. Okay, so it's u cubed cosine v sine v root 2u dA. Okay, a lot of work just to set this up. Not too hard though. We can take this and we can write that down there. So it's u goes from 0 to 2, and one more time, v goes from 0 to pi over 2. So this is important. This is going to be the integral from 0 to pi over 2 first. If you want to, or the other one first, it's fine. And this is root 2u to the fourth. I'm factoring this root 2u in. Well, what am I saying? You can't really factor it in. It's just one term. So just multiplying it. Root 2u to the fourth cosine v sine v. I'm really tempted to stop the video here and call it a day and just ask you to integrate, but I'll just do it. That's fine. It's good practice. Okay, yeah, I'll do it. So remember that we're not done with the setup also. So the setup is just gonna, oh sorry, this is gonna be d. Now we will be done with the setup, du dv. Now we're done with the setup. This is the integral you gotta evaluate, but there's a way to split this up, and I'll do that. And the reason why is because we're going from constant to constant for both of these, and they're being multiplied together like the way they are. So you can split this up into the integral from 0 to pi over 2, and then we can just take the v's, because this is dv, so you can just take the v's. That's cosine v sine v dv, and then just multiply that with the integral from 0 to 2. That was thicker than it should be, but root 2 u to the fourth du. That's completely, this is completely equal to this guy. It's completely equal to this thing over here, being gender neutral. This thing over here. So let's compute that. This some, for some people this is obvious and they can do this in their heads. I personally probably can't. I'm just gonna try to use the u sub real quick. So u is sine v in this case, du is cosine v dv. This is a nice way to set this up. So u is sine v, so we'll just take that u, and then cosine v dv is du, and then integral sine 0. So sine of 0 is just 0, and then sine of pi over 2 is 1. 0 to 1. That's that. And then multiply that by this guy, this thing. It's going to be, well, let me actually go ahead and just write it again, and we'll integrate it in the next step. And it's funny because it looks like this is a u, and this is not the same u that we see here. It's different. I probably should have used a different variable, but it doesn't matter because, again, we're just using this as a temporary variable, so it doesn't matter what we use. We're gonna get the answer for this and the answer for this, and we're just gonna multiply. So no matter what variable you use, u to the 4th du. I'm very tempted to change the variable now, but at the end of the day, even if I use like an n, for example, I'll get the answer to this. Even if I use u, I'll get the same answer. So it doesn't matter, but it's just kind of for being more kind of organized and making sense of my variables. But at least I've mentioned it, so I'm just going to continue. So this is u squared over 2, 1 to 0, times, this is also not that hard, it's root 2 over 5, u to the 5th. 2, 0, 0 to 2. 0 is not going to worry about, it's just 1/2. And then same thing here, 0 is just going to be 0, so it's going to be root 2 over 5 times 2 to the 5th power. This will cancel with this, becoming 4. 2 to the 4th power is 16. So this is 16 root 2 over 5. That is the surface integral computation, and that's the answer. So on a test or on a homework assignment, this would be a nice detailed work that you could show, hopefully for full credit.